So today's date is 22/2/2022. Very nice date, right? Okay, is Rohit Dharavia present in the class currently? Roll number 33. So he has not joined the class. So please inform him that he should join, can perform the submissions. Okay, so we will continue from our discussion of advanced encryption standard. AES, a very short revision of last week discussion about AES, and then I will start again the discussion of finite field structure. Right. So advanced encryption standard is a symmetric block cipher which encrypts 128 bits at a time. It is a non-fistal type, as the basic elements of AES are all invertible. In fistal type structure, like in DES, there are elements which are non-invertible, right? So non-fistal has all elements invertible. Okay, am I audible, students? Can you hear me? Okay, okay. So it has three versions, AES 128, 192, and 256, where the key size is 128 bit with 10 rounds, 192 bits with 12 rounds, and 256 bit with 14 rounds. But the round keys are always 128 bits. So this key size is cipher key. Round key are of 128 bit. Block size is 128 bit. Okay, so the plain text is given as an input to 128 bit block. There are NR rounds, K1 to KNR rounds, plus one pre-round. Okay, so the keys are KNR plus 1, right? K0 to KNR. So NR plus 1 into 128. So this many total bits are used to encrypt. So you can see in this block key expansion, cipher key 128, 192, 256 bits, and that gives you 128 bit key, and then you have ciphertext. Okay, now there is a byte concept. This is fundamental of computer science, right? So 8 bit is a byte, so B0 to B7. Word are of 4 bytes. So the size of one word is 4 bytes, that is 32 bit, and one block is of 16 byte, so 128 bits. So block is numbered from B0 to B15. Each one is byte, so 16 into 8, that gives you 128 bit. So it is arranged as a matrix of 4 cross 4, B0, B1, B2, B3, B4, B7, B12 to B15. The state is S00, S01, 2, 3, and up to S33. Now Sij is a byte. So in a matrix of 4 cross 4, each element is byte. And we had seen that the text AES uses a matrix. AES, A is 00, E is 04. Now this is modulo 26, right? So you represent each byte as each number as a byte. So instead of 0, we write 00 to indicate it as a byte, and it is written in the hex. Okay, so the values represented are hex values. Now the structure of each round is sub byte, shift round, shift row, shift mix column, add round key. All this I have already discussed, so I'm not repeating it. Here we need a concept of byte, sub byte, right? So that is why we started discussion of finite field. So today I intend to finish this finite field discussion. What is a field? It is denoted by F set. One operator is dot operator and second operator is square operator. So we assume that these are two operators. Later on, when we will define a field or we'll use the field, we will use this first operator as plus, second operator is multiplication. It could be any operator. So we can define this field over this operator is a commutative ring in which the second operation satisfies all operations except that the identity of the first operation has no inverse. Identity of the first operation, right? So we have to see that this is the first operation, first operator, and it follows, it satisfies five properties: closure, associative, identity, inverse, commutative. And you have already studied this concept in your elliptical curve cryptography, right? So you understood the concept of closure, associative, identity, and inverse. Uh, that makes what is the structure, what it is called as when it satisfies these four properties. In elliptical curve cryptography, there is a concept of group and there is a concept of abelian group, right? So that in that context, you have studied these properties and they are applicable over here. For second operator, all the properties except the inverse and the identity operator of the first operator, identity of the first operator doesn't have inverse in the second operator, right? So the identity of the first operation has no inverse with respect to the second operation, right? So this is the relaxation. Second is that there is a distributive, second operator is distributive over first operator. So that distributive property is also satisfied and that makes it a field. So apart from these five properties, distributive property is added. So a second operator, a square b dot c, that is a square b dot a square c, it satisfies this. If it satisfies this property, then it is called as a field. So there is a, from field, there is a concept of finite field. So it is a field with finite number of elements, and finite fields are very important structures in cryptography. And Galileo showed that for a field to be finite, the number of elements should be p raised to n, where p is prime and n is positive integer. So the finite fields are usually called as Galileo's fields and denoted as GF p raised to n. This Galileo's field discussion, I think, also came in the discussion of elliptical curve cryptography, but we will discuss the exact definition of okay, I'm back now. My connection got disconnected, but now it is okay. Okay, students, can you see this? Is the slide, is this screen visible to you? Okay, okay, good. So GFP fields, this field can be the set ZP equal to 0, 1, 2 up to P minus 1 with two arithmetic operators or operations, addition and multiplication. Here P is prime number, okay? P is a prime number. So the first prime number, so we take 2, GF2. So the elements 0, 1, it's a binary. So 0, 1, that is, these are the members of the set. Okay, as you know that the definition of the field says first is set, second and third are operators. So here the first set is having two elements 0, 1, and the operators for these elements are plus 2, star 2. That means addition on this binary number and multiplication on this binary number. So here addition is XOR and multiplication is AND operation. Right. So let us see how the addition is carried out on these elements. So in row we have 0, 1, and in column we have 0, 1. Row we have 0, 1, and column we have 0, 1. So 0 plus 0, that means 0 XOR 0. So that is 0. 0 XOR 1, that is 1. Okay, 1 XOR 0, that is 1. And 1 XOR 1, that is 0. That you are aware about, right? So here we have 0. So if you add any element to 0, you get the same element, right? And if you multiply, so 0 multiplied by 0 is 0, and 0 multiplied by 1 is 0. 1 multiplied by 0 is 0, and 1 multiplied by 1 is 1. So here you get additive inverse. 0 is additive inverse and 1 is multiplicative inverse. And for 0, in the multiplicative inverse, you don't find any inverse. That means an additive inverse, multiplicative inverse is not available. Now, if you take GF5, so you have 0, 1, 2, 3, 4. Now, if you try to find out the closer associative that is going to be satisfied, you have already gone through that. That closer associative, identity, inverse, commutative, all this, the plus operator satisfies that, star satisfies all except the additive inverse identities of the identity of the first operation has no inverse. So plus has no inverse, plus 0 has, 0 is the identity over here, and 0's inverse is not available. So that satisfies. So this way we checked. Now we take another example of GF5. So GF5 has how many elements? GF5 has how many elements? If we take 5, which elements we have to take? Yes, please respond. 0, 1, 2, 3, 4. And this 0, 1, 2, 3, 4 are mode bit, mode values, or just some number value? It is mode value. Yes or no? Which mode? Mode 5, right? Mode 5, right? Okay. So if you look at this first, whether now we check whether it satisfies Galileo's field. So we take two operators, plus and second operator is multiplication. And here, so these two operators are different. In GF2, we have plus 2. That means plus operator over modulus 2. And here, plus operator over modulus 5. So these two operations are different. Okay, don't consider these two as same. You have to understand it, right? These two operators are different. This star is different, and it is defined as per this table, right? So you can see you have 0 to 4 rows and 0 to 4 columns. So 0 plus 0 is 0, 0 plus 1, 2, 3, 4. So it remains same, right? Similarly, column. So first row and first column is same as input. That makes 0 as identity. Now, if you take 1 XOR 1, right? 1 plus 1, that is 1 XOR 1. So that is 2, right? 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. Now 1 plus 4, 1 plus 4 is 5, and 5 mod 5 is 5 mod 5 is 0, right? So here why we have taken this 1 plus 0 is 1, 1 mod 5. 1 plus 1 is 2, 2 mod 5 is 2, 1 plus 2, 3, 3 mod 5 is 3, right? So this way. Similarly, if you take 2 plus 0, that is 2 mod 5, 2 plus 1, that is 3 mod 5, 2 plus 2, 4 mod 5, 2 plus 3, 5 mod 5, that is 0, and 2 plus 4, that is 6. So 6 mod 5, that is 1, right? So if you calculate this, third and fourth and fifth row appears to be like this. And if you observe this, it is actually a left shift operation. So in the second row, this row goes to the last element. In the third row, this element goes to the last, right? So it is shifting left one by one place. Similarly, here if you see multiplication, so 0 multiplied by 0 is 0. So if you look at all these elements, anything multiplied by 0 is 0. And so first row and first column are all zeros. Okay, now if you take 1, anything multiplied by 1 should be 1, right? So 1 mod 1 is 1, and 1 mod 5 is 1. 1 multiplied by 2 is 2, 2 mod 5 is 2. 1 multiplied by 3 is 3, 3 mod 5 is 5. And 1 multiplied by 4 is 4. So 4 mod 5 is 4. Now if you take 2, so 2 multiplied by 0, 2 multiplied by 1, 2 mod 5, 2 multiplied by 2, 4 mod 5, 2 multiplied by 3, 6 mod 5, that is 1, and 2 multiplied by 4, that is 8, 8 mod 5 is 3, right? So 1, 2, 3, 4, 1, 2, 3, 4. Similarly, 4, 1, 3, 4, 1, 3, 4, 2, 4, 2. And the last one is 4 into 4, that is 16. 16 mod 5 is 1. So if you see this 1, so in the second row, you find 1 over here. Third row, you find 1 over here. Okay. Fourth row, you find 1 over here. And fifth row, you find 1 over here. It means that in the second row, you have this as an inverse. Third row, you have this. So 2 and 3 are inverses. 1 and 1 are inverses of each other. 3 and 2 are inverse of each other. 4 and 4 are inverse of each other. So you find identity and the multiplicative inverse, but you don't find multiplicative inverse of the identity of the first operator, because here you find that all are zeros, right? So additive inverse of, as per this table, is for 0 it is 0, for 1 it is 4, for 2 it is 3, for 3 it is 2, for 4 it is 1, right? So these are the additive inverse, and multiplicative inverse we have to locate 1. So 0 we don't have, 1 we have 1, for 2 we have 3, and for 3 you have 2, and 4 we have 1, right? So this GF5 is Galileo's field, because it satisfies all 5 properties. We have to also see that it is satisfying closure, associative, and commutative. Then Galileo's field is finite field, or it is a Galileo's field. But if you see GF4, it is not a field, and because 4 is not prime, and we can show that that 4 is not a prime, right? So this Galios field is having first is set, that is ZP, where P should be prime. But if we take 4, then we have Z4, right? So 0, 1, 2, 3. No, 0, 1, 2, 3. Yes, 0, 1, 2, 3, right? So you can do that exercise. Now we talk about important concept which is required for finite field, that is GF 2 raised to n field. Now computers have n bit words. Okay, generally if you buy any processor, you ask what is the processor. So in old days, there used to be 8-bit processor, 16-bit processor, 32-bit processors. These used to be considered as very good processors in those time. Nowadays, we have 64-bit processor and higher processors, right? So GF, so we need actually in computer, we need the values which can be represented by 2 raised to n. And that is why we are taking in Galios field 2 raised to n. Okay, so 2 raised to n is a field with operation XOR and polynomial multiplication with respect to prime number. So plus operator is XOR and multiplication is polynomial multiplication with respect to prime modulus, right? So we define two operator for 2 raised to n Galios field, where the first operator is plus, that is XOR, and second operator is polynomial multiplication. We are not saying simple multiplication, we are saying over here polynomial multiplication with respect to prime modulus. And this modulus concept, polynomial concept, that you have already studied in cyclic redundancy check in computer network. Have you studied that in computer network? Cyclic redundancy check. Yes. Am I audible? Are you there? Have you studied Ayush cyclic redundancy check in computer network? Okay, so you understand the polynomial operations, right? So those operations you will have to do it today in the class, right? So you keep the pen and paper with you. It will not be just easy for you to read and understand. You should practice this. Okay, so let's start with the polynomial representation of the 8-bit number. So if we have n-bit word, then it can be represented by x raised to 0 to x raised to n minus 1. So if we have 8-bit word, then we have 8 bits, and so the bits are represented in the form of polynomial term having exponent 0 to 7, that is n minus 1, right? So n equal to 8. So we write x raised to 0, x raised to 1, x raised to 2, x raised to 3, up to x raised to 7. This is from left to right. Okay, so just a minute. Okay, now see what happens. Our 8-bit number is 1001 1001. Okay, now we want to represent this number as a polynomial. So what we do, we write this polynomial x raised to 0, x raised to 1 with respect to each bit, and we can represent a polynomial as ax raised to n minus 1 plus bx raised to n minus 2 plus cx raised to n minus 3 up to d x raised to 0. That means d itself. So the last term is constant, right? So here what we do, we multiply this number with the exponent because we want polynomial, right? So yes, Ayush, very good. So 1x raised to 7 plus 0x raised to 6 plus 0x raised to 5 plus 1x raised to 4 plus 1x raised to 3 plus 0x raised to 2 plus 0x raised to 1 plus 1x raised to 0. And what we get is x raised to 7 plus 0. 0 into anything is 0. 0 into anything is 0. So this term is also 0. This term is also 0. The remaining is 1, x raised to 4, x raised to 3, and x raised to 0 into 1. So here plus means XOR. So in this polynomial, plus is actually XOR. So what we are getting is that this number, 8-bit number, can be represented as a polynomial of these 4 terms. X raised to 7 plus x raised to 4 plus x raised to 3 plus x raised plus 1. Okay. Now find 8-bit word allotted related to x raised to 5, x raised plus x raised to 2 plus x. So now we are given the reverse of this. Suppose if you are given 8-bit word, then you have to convert it into polynomial. This is one example. Now the reverse example, you are given a polynomial and you have to get this number. Okay. So I suggest to each one of you to try it. Can you try it? What is the number which is represented by this polynomial? X raised to 5 plus x raised to 2 plus x. Can you do it? See, it is 8-bit word, right? So that means you have to represent x0 to x7 with coefficients. So wherever you find the term, your exponent, your coefficient is 1. And whenever you don't find any term, its coefficient is 0. So this way you have to find a number. So will you please try and type it in the chat box? Have you really understood it or not tried? Okay, Ronak. X raised to 0. See, the last bit is 1. Okay, Urjit. Okay, Urjit. Yes, Ayush. See, Ayush, last bit is 0, right? So, in this polynomial, you don't find last term as 1. And so, x raised to 0's coefficient is 0 because x raised to 0 is 1, right? So, what you have done is correct, right? Now, x raised to 2, x raised to 1, that is x. Okay, so the coefficient is 1, right? So that is why this term x is valid. And so the second last bit is 1. Now third last bit is x square, right? So x square into 1, that is x square. So the second last bit is also 1. Then x raised to 4, x raised to 3, x raised to 4 are 0. Then x raised to 5 is 1. Okay, x raised to 6 and x raised to 7 are 0. And that is why we have the number 0, 0, 1, 0, 0, 1, 1, 0. Right? 0, 0, 1, 0, 0, 1, 1, 0. Okay, you can see in this note this x raised to 7, 6, 4, 3, and 0. These all are having coefficient zeros. But the 5, 2, and 1 are having 1. Now there is a concept called irreducible polynomials. Like when you do modulus, okay, there are some reminders which are remaining reminders, right? So those reminders are actually not possible to be included. So here in the polynomial, there is a concept of irreducible polynomial. So it cannot be factored. Here the polynomial is irreducible. It means it cannot be factored. If you have a polynomial which can be factored, it is reducible. But if you have a polynomial which cannot be factored, then it is irreducible. And it has a power of providing you the security. So these polynomials so it cannot be factored into a polynomial with degree of less than n, and so it is also known as uh, prime polynomial. Okay, so the list of irreducible polynomial are given in this table. See, you can see in this table that for degree 1, 2, 3, and 4, so these irreducible polynomial are actually represented as a Gaussian field, because if you see GF2 raised to 2, for that GF2 raised to 0, that is 1. For that, the irreducible polynomial are x plus 1 and x. For GF2 raised to 2, we have irreducible polynomials are x square plus x plus 1. 2 raised to 3, we have x raised to 3 plus x square plus x, and x raised to 3 plus x plus 1. So if you see that degree is 1, that means that degree of x should be the first term. Okay. So second, you have degree 2. So the first term is x raised to 2. Degree 3 means first term is degree 3. And fourth term is first term in the fourth table row of the table is that the first or the highest degree is x raised to 4. So if you see this polynomial x raised to 4 plus x3 plus x square plus x plus 1 and x raised to 4 plus x3 plus 1, these two are irreducible polynomials of degree 4, irreducible polynomial of degree 3. And why we are discussing this? Because we will need this in our AES. So that is why we are discussing this topic. So GF of 4, okay, that is 2 raised to 2, this second, right? So it has Z4. So Z4 means how many elements? Which elements? In Z4, which elements are there? Yes, you have studied this in first sessional, first week itself. Z4. Z4 means 0, 1, 2, 3. Very good, Janil, Deep, Morkar. So Z4, and the operators are XOR and multiplication. So this operator is plus 4 and star multiplied 4. That means the result is modulus 4. Okay. So we have 4 elements 0, 1, 2, 3. Now we want to represent this element as a polynomial. So to represent this polynomial, we have to first represent it as a binary, right? So if we write 0, so the decimal 0 is equivalent to 0, 0 in binary. So 0, 0, if we take it as a coefficient, x raised to 2, 0 into x raised to 2 plus 0 into x raised to 1, right? So that is, or 0 into x raised to 1 plus 0 into x raised to 0. but that gives you the same result, right? Now, 1 for 1 we have 0 1. So 0 1 means x raised to 0 multiplied by 1 and x raised to 1 multiplied by 0. So it is 1, right? So for 1 it is 1, for 0 it is 0. Now 2. 2 is 1 0. You can see 2 in decimal is 1 0 in binary. So 1 0 is equivalent to x raised to 0 into 0, that is 0, plus x raised to 1 into 1, that is x, right? So 2 is actually represented as a polynomial x. 3 is represented as a polynomial of the same degree x plus 1, that is 3 is binary 1 1. So 1 into x raised to 1 plus 1 into x raised to 0. So that is x plus 1. So we have found four elements of GF4 and which are over this operator. So now let us see whether these operators are satisfying all the properties of field structure. So commutative, associative, identity, inverse, and closure, right? So we have you can do the self analysis of the all the operations except the second and third, that is identity and inverse, right? So identity and inverse. So let us see plus operator, that is XOR. So here we see 0 XOR 0, that is 0. 0 XOR 1 is 1. 0 XOR x is x, and 0 XOR x plus 1, that is x plus 1. Similarly on the first column. Now if you take this 1 XOR 1, that is 0. Okay, 1 XOR x is x plus 1. 1 XOR x plus 1, that is 1 x plus XOR x XOR 1 XOR 1. So 1 XOR 1 is 0. So x XOR 0 is x, right? So we get this 1 plus x plus 1 is x, because 1 plus 1 or 1 XOR 1 is 0. Okay, now multiplication. Now if you see in this plus operation, wherever we have addition with 0, we get the same element, right? So 1 XOR 1, that is 0. And x XOR x, that is 0. And x plus 1 XOR x is x plus 1, that is 0. Because x plus x is 0 and 1 plus 1 is 0. Is that clear? Yes, understood. Please respond. Yes, students. Deep Morkar, have you understood? Ayush? Ayush? Okay, okay. Right, so here 0x as identity. Now here multiplication. So 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. So all first row and first column are 0, because anything multiplied by 0 is 0. Anything multiplied by 1 is 1. So 1x x plus 1, 1x x plus 1, and 1x x plus 1. Now third row, x multiplied by 0 is 0, x multiplied by 1 is x. Now third is x into x. So x multiplied by x is x square. But is x square member of Z4? Is x square member of Z4? right? So what we have to do is we have to multiply, we have to divide it by the polynomial, right? So x square is x square mod prime polynomial of degree 2. Which element, which one is the prime polynomial of degree 2? X square plus x plus 1. So at that time we have to take this x square plus x plus 1, that is prime polynomial. So we have to divide x square by this, right? So x square cancels out. So what remains is x plus 1, right? So the result is that it is x plus 1. Okay, so this is very important thing. Now let us take the next x into x plus 1. So x into x plus 1, it is equal to x square plus x. So x square plus x is not in the set of elements 0, 1, x plus 1. So we have to take modulus with respect to prime polynomial. Prime polynomial of degree 2 is x square plus x plus 1 so x square plus x does not belong to this. So we need to do x square plus x mod prime polynomial of degree 2. So x square plus x is divided by x square plus x plus 1. So we take 1. So x square plus x plus 1, where this x square and x cancels out. So what remains is 1. So here if you see, x plus 1 into x plus 1 is x into x plus 1 is 1, and x plus 1 into x is also 1. Now last one is x plus 1 into x plus 1. So x plus 1 into x plus 1 is x square plus x plus 1, right? So x square plus x plus is XOR, so x XOR x, that is 0. So you have x square plus 1. So x square plus 1 again doesn't belong to this element set. So we have to take modulus with respect to irreducible polynomial. So x square plus 1 divided by x square plus x plus 1. So if you multiply it by 1, what remains is x square plus x plus 1. So x square and 1 gets cancelled out. What remains is x. So you have this x. Okay. So since plus is a satisfying all properties and star also satisfy all 5 properties, and plus and multiplication is distributive over plus. So a XOR a multiplied by b XOR c equal to a multiplied by b XOR b a multiplied by c. Okay, this is, remember that it is modulus 5 with respect to Z4. So A and B should be with respect to Z4. How these properties are satisfied? Closure, identity. So if you look at 0, anything plus 0 is 0. Anything plus 0 is same value. And multiplication, wherever you find multiplication, you have multiplicative inverse. Priyank, you are saying x square. Okay. Priyank, have you understood this x square plus x? how we have obtained this 1. So similarly here, instead of x square plus x, if we have x square alone, then also x square plus x plus 1, if we keep this, we have here x square plus x plus 1. So only x square gets cancelled out and what remains is x plus 1. Is that clear, Priyank? Okay, Urjit, how 1? It should be -1 as we change the sign for cancelling the term. Okay, I think I have, okay, this is the last point here, that plus is XOR as well as minus is also XOR. So when we are doing minus over here, it is actually XOR. That's why it is cancelling. Is that understood, Urjit? Okay. So yes, so it like what you used to do in Z26 or Z5. If you have Z5, if you have, let's say 8, can you represent 8 in Z5? So what will be the value? If you can recollect congruence, congruence we discussed in the beginning, 8 mod 5 is what? 8 mod 5 is? Yes, Priyank. What is 8 mod 5? 3, right? So 3 congruence 8. Do you remember this? 3 congruence 8 in Z5. Right, so this is exactly the same thing, but instead of an integer number, we have a polynomial. So x plus 1 is x plus 1, but x square is also x plus 1. But x, so we
Hello,
can
sir.
x square as congruence to x plus 1. In Z, here, which Z we have taken? Z4. Z4, I think we have written. Z4, yes, Z4. So in Z4, it is x square is x plus 1. Both are same because it is Z4. Clear? Okay. So let us move ahead. So here I was talking about this 0. 0, if you add anything to 0, 0. But if you multiplied, now see where you are getting 1. So 1 multiplied by 1 is 1. X multiplied by x plus 1, that is 1. So this is multiplicative inverse. So we can say that x and x plus 1 are multiplicative inverse. So 1's multiplicative inverse is 1. X inverse is x plus 1 and x plus 1 inverse is x. So where you find 1, that becomes inverse. We don't have minus value here. We have XOR. We have not defined minus. Our minus and plus both are XOR. Clear? Okay. So we move to the next. So here we have identity and inverse. So that is represented as XOR. That is what I have written over here. Plus is XOR and minus is also XOR. If you see XOR operation, it is doing both. Okay. So this is what we have done, x square plus 1. So what we find is x. So plus is satisfying all five properties, multiplication is satisfying all five properties, and multiplication is distributive over plus because a multiplied by b plus c is a multiplied by b XOR a multiplied by c, where ABC belongs to Z4. Okay, so thus with respect to plus, first operator plus, second operator multiplication gives set, given set is filled. So Z4 is a Galileo's field. Okay, now in AES we will use this 2 raised to 8 field. Okay, GF 2 raised to 8 field, and that is why let us see how this 2 raised to 8 with respect to these operations. Okay, we will discuss this in a short time. So remember, this is very important point. In AES, we use Galileo's field 2 raised to 8. Okay, and prime polynomial is 2 raised to 8. And so the polynomial is, prime polynomial is x raised to 8 plus x4 plus x cube plus x plus 1. That you can see over here what we listed for 2 raised for x raised to 8, right? So this is the prime polynomial. For this is the important polynomial for us, x raised to 4 plus x4 plus x3 plus x plus 1. Now let us see, let us do this example. X raised to 5 plus x square plus x multiplied by x raised to 7, x raised to 4, x raised to 3 plus x square plus x in GF 2 raised to 8 with prime polynomial this. So this is very important point, and we will have to do it in the AES. So when we multiply this 3 term with these 5 terms, we get 5 into 3, 15 terms. So in these 15 terms, you see x raised to 5 multiplied by these 5 terms, x raised to 2 multiplied by these 5 terms, and x multiplied by these 5 terms. So what we get is x raised to 12, x raised to 9, x raised to 8, x raised to 7, x raised to 6. That is this first row. This x into x raised to 2 into x raised to 7, that is x raised to 9. So x raised to 9, x raised to 6, x raised to 5, x raised to 4, x raised to 3, and the third row is like this. So here you see that this plus is XOR. So x raised to 9 XOR x raised to 9 is 0. X raised to 8 and x raised to 8 XOR 0. X raised to 7, x raised to 4, sorry, x raised to 6 and x raised to 6 cancels out, x raised to 5 cancels out, x raised to 4 cancels out, x raised to 3 cancels out. So what remains is x raised to 12, x raised to 7 and x raised to 2. But this degree is greater than the degree of 8, and we have to find it with respect to 8. X raised to 8 plus x square, x raised to 4. So the highest degree is 8. But here this polynomial which we have found is 12. So it is clearly greater than this. So we need to divide it with this prime polynomial. So x raised to 12 plus x7 plus x2, that is divided by this prime polynomial. And so what we get is, here we have x raised to 12. So we multiplied by x raised to 4. So x raised to 4 plus x raised to 8. So x raised to 12, x raised to 8, 4 plus 4, 8, 4 plus 3, 7, 4, 3, 1 plus 4, 5, and 0 plus 4 is 0, x raised to 4. So this x raised to 12 and x raised to 7 cancels out, and what remains is x raised to 8 plus x raised to 5 plus x raised to 4 plus x square. Now again we divide this, so we take 1, so x raised to 4 plus 1, and what remains is this, and here x raised to 8 cancels out, x raised to 4 cancels out, and what remains is this. Now this is actually less than 8, having degree less than 8. So we can say that it is a prime polynomial of degree less. So now find this another example, x raised to 2 plus 1 inverse with respect to modulo x raised to 4 plus x plus 1, right? So this is in GF 2 raised to 4. So GF 2 raised to 4, we have to take irreducible polynomial from 2 raised to 4. Okay, so that we have taken here. 2 raised to 4 has this polynomial x4, x 3, x3 and 1, or x4, x3, x2, x1. These are two irreducible polynomial. And if we see here, we have to find the inverse of x square plus 1. So we will use the same method as we applied in the modulo arithmetic. In modulo arithmetic, we applied this concept of Euclidean algorithm, extended Euclidean algorithm. So the same algorithm we will use here. Here we have x raised to 4 plus x plus 1, that is R1, and x square plus 1. This term's multiplicative inverse we want to find with respect to this. So we multiplied by x square. So x square, so x raised to 4, it gets cancelled out because it is XOR operation. Then x square. So x square plus x plus 1, again x square plus 1. So what remains is x. So the remainder is x. Okay, and similarly t1 and t2 and t. So t1 is 0, t2 is 1. So t1 minus q t2. What is q? Q is x square plus 1. So 0 minus x square plus 1 into 1. But minus is plus because XOR, both are same. So here we write x square plus 1. Okay. So x square plus 1 is the first iteration. Now what we do, we shift. So our R1 is x square plus 1 and R2 is x. Okay. The remainder becomes x. So that becomes R2. So x square plus 1 divided by x. So we take quotient x. So what we get is 1. And we have found R equal to 1. So t equal to t1 minus q t2. So that is 1 minus x into x square plus 1, but minus is plus. So x into x square plus 1, that is x cube plus x plus 1. So this is the t. So we again shift R1 equal to x and R2 equal to 1. So we have found that R2 1. So at that point, t equal to t1 minus q t2. So t1 is x square plus 1 minus x into x cube plus x plus 1, minus is plus. So we follow this operation and what we get is x raised to 4 plus x plus 1. Now if we take modulus of this with respect to the same prime polynomial, then we get 0, right? So now again we shift 1 and 0. So what we find is that we have found that R1 is 1. So at that time T1 is x cube plus x plus 1. Okay, T1 is x cube plus x plus 1. So x square plus 1 has an inverse, that is x cube plus x plus 1. Okay. Now this is with respect to modulo x raised to 4 plus x plus 1. Okay. Now if we want to do verification, if we multiply these two terms, what we get is this. Okay. And if we take prime polynomial, take modulo with prime polynomial, we get 1. So if the two are multiplicative inverse, because the multiplication of that gives you 1, right? So the inverse is correct. Now similarly, another example, and I will give you this as an assignment, but quickly I will discuss x raised to 5's inverse in GF2 raised to 8. So our polynomial is x raised to 8 plus x 4 plus x cube plus x. So if you see this, R1 is this polynomial, R2 is x5. We follow the Euclidean algorithm. So Q is x3. So what we get is, if we divide this, we get x raised to 8. So what remains is this. Now, again, we shift it. And at that time, T1 and T2 are 0, 1. So T3 equal to, if T1 minus Q T2, so that is x4 plus x cube plus 1. Now x4 plus x cube plus 1, that should be written over here. Okay. Now shift operation is carried out. So what we get here is x4 plus x5 comes over here, x4, x3, x1 comes over here. And when we do this operation, x raised to 5 divided by x cube, x4, x3, x1, x1. So we multiplied it with x plus 1, we get x cube plus x square plus 1. So that we write over here, right? And then again we shift it, and finally when we obtain 1, at that time, what value of t1 we get is x5, x4, x3, x. So x raised to 5 is inverse in gf 2 raised to 8 is this. Okay, so I hope that you will be able to solve this in the next class. A quick revision of only this example I will carry out to cover it with AES. Okay, so I stop here. Code you have to submit with output. Check in the classroom. Yes, I will share this PDF.